The idea today is to share with you what machine learning can bring to mining operations in particular. There's been a lot of other applications being discussed. We're going to focus particularly on operations. And if we talk about operations, data analytics is not a new thing in mining. It's been used for quite some time. First, it was through computational support for different applications, and getting from equations to actually doing advanced calculus. That was the first use of analytics in mining. Then it was discrete event simulation. And now we're at a frontier where we're moving towards AI and machine learning. So I'm going to go very quickly through this. As you know, machine learning is part of AI. In general, is a technique used for AI. And there are different techniques used in machine learning, the most widely popular being neural networks and deep learning. But the thing is, OK, this is a fantastic tool. I can use it to analyze big chunks of data. So why is it so relevant for mining and for mining operations in particular? So if we think about how we optimize and move through getting the most out of our operations, typically the traditional approach was defining models to try to identify optimal points of operation. But those models were based on predefined equations. So to some extent, we needed some knowledge getting into the operation. And not many times we were able to reflect the exact nature of the operations. Machine learning models are different in that sense. They don't need a predefined equation. They just learn from the data. They learn the relationships from the data, and they are able, for that reason, to get to much more accurate models of reality. So here's an example. This is what I'm showing here is basically the throughput in tons per hour. That's what you see in the y-axis. And in the x-axis, what you're seeing is load of a SAG mill. The different colors in the curve on the left is actually different throughput and different load for different speeds for the SAG. Okay, 9.7 RPM, 9.5 RPM. This is for a copper operation. That is what we get when we use parametric definitions of how we can optimize our operations. The one on the right was generated with machine learning. We did not tell in any way to the model how it was supposed to work. So the model figures out the relationship on itself. And in doing that, incorporates some effects that are not captured in parametric models. The most notable one, particularly in SAG mills, is the age of the liner, for instance. As you know, at least in large copper mining SAG mills, liners are changed every 6 months. It's very difficult to get the age of the liner as part of the parametric definition on where can I operate in an optimal level. The model does that by itself. And here what you can see is to the right, we have more data density. That's why the gray area turns smaller. That's why the model has better confidence when it has seen the data. It can make inferences for very little load. But of course, because this was from an actual operation, they were operating with plenty of load. So that you don't have enough information there to make an accurate observation. So how is it that this helps us? Getting more accurate models can allow us to make model different decisions, and of course, trial and error in the digital world, not in the real world. But doing this is much more accurate than the way we have been doing things in the past with traditional and parametric models. Okay? So in the end, it will allow us to make better decisions. The two key things that are really valuable about machine learning models is that allows us to make predictions, but also inferences. One of the most useful things we've done with machine learning models is to actually build inferences and what we call it's a partial effects plot to understand, for instance, what's the exact impact of granulometry and fragmentation in a SAG throughput. Taking out and cleaning the effect of all other variables, or hardness, liner age, speed, percentage solids. So you can start to take apart stuff and understand how things are interrelated. But it's not all roses for machine learning in mining. And this is a critical thing, and I'll revisit this towards the end of my presentation. But machine learning also has limitations. Okay? The number one limitation is quite obvious, which is data. Because the model learns from data, it can't learn from data that it hasn't seen. So if for some reason you have a new operation or you have a new phase of the mine that will see significantly different type of ore, the model that you build with the current information won't be as valid. Many times clients ask us, but my operation is quite unstable, so I won't be able to learn anything about from the machine learning model. Actually, that's much better. What the model would not be able to learn if it was just stable all along. If you have just one speed, one level of hardness, one level of fragmentation, then the model learns nothing. Okay? So variability is good for machine learning. But of course, lack of data, it's not. And lack of areas where it hasn't seen data, it's not. And the second thing, and this is extremely important, is that it is not Skynet. Okay? It won't answer questions that you can't ask the model. So you need to come to the model with hypotheses. And let me put an example that really illustrates this. So we work with this was actually done with Costa, with this number 2 copper mine in the world. And we built a machine learning model of the SAG. I'll share in a second. And the VP of operations tells me, OK, it's surprising that the model doesn't tell me that on the first day of the shift, which is on Tuesdays, I usually would have expected to be a driver of slightly lower throughput, because you have the shift handover and some things happen particularly on that day, so it's usually the case. But because we didn't have that hypothesis, when we entered the data and we built the model, we didn't put a flag to mark that this was the first day of the shift. So therefore, if we didn't have the hypothesis, the model is not by itself going to be able to magically answer that question. So it's very, very important that this is not just about the data. It's about understanding where the problems are and what are you trying to fix with it. And so by doing this and by applying this technique, you can get into basically every step of the value chain in mining, from exploration and using machine learning to understand and identify patterns in exploration and prospecting much better, improving fragmentation, giving, doing models for the type of ore and the fragmentation that I get out of the blast design parameters that we can give input. Of course, maintenance performance and preventive maintenance using machine learning to understand how a truck might fail. But I'm going to focus on the next two, in crush and grind and in concentration and in smelting. And why is it that I'm going to concentrate on that, and why is it that machine learning gives so many insights into these processes? Because it's processes where several variables get together at the same time, like I mentioned before, hardness, fragmentation, speed, percentage solids, several decisions that are taken by the operator or by control systems, and one output, typically recovery and throughput. Okay? So let's get into a specific example. I guess this is so far been interesting, but it's more of the theory. So now let's get practical into how this can be applied and how we have applied this to copper miners, particularly in this case in Chile. So you know already what a SAG mill is. This is one of the largest copper SAG mills in operations in Chile. As you know, this, even though it's a mechanical process, it's very much controlled with a lot of technology, control systems that with certain inputs and with certain ranges for the optimal parameters, looks to improve and to drive the best throughput, right? But then, and this is probably very much the same for the producers in the room, what you would get out of a similar graph if you do it yourself, the treatment per hour changes significantly, right? It's not very stable. Many times we know for some reason why it has gone down. Maybe we're processing harder ore. Maybe they are blasting with an explosive product that is not as powerful, and we're getting lower fragmentation. But then how can we optimize this? If there's always something about it, how can we optimize this? We expect an expert system to do it by itself on the SAG mill, but it's not using techniques as advanced as machine learning. And it's difficult because, as I mentioned before, you have several variables affecting simultaneously, and many times you have several decisions taking place at the same time, many times by different areas of your company. Sometimes it might be the mine guys that say, oh, I'm going to do more blasting, and I'm going to do a favor to the SAG guys and to the mill guys to process more ore. But there are also decisions taken at the mill operation with speed, with load, and with the percentage solids that can get into the SAG. So what is it that we do? That we did? We did this machine learning model. We identified and lifted over 400 variables, 3 years of data, and in most cases, data points were available with a 1-minute interval. In many cases, even more frequent. If you do the math quite quickly, it gives you way over 500 million data points. So this is very hard to process for something that is not machine learning. And the model then allowed us to understand and experiment. And let me show you an example. Here is, and I'm showing here 25 consecutive days of data for hardness and fragmentation. This is actual data. Then we say, OK, let's control for one variable. And the model allows us to do that. Here we're controlling for ball charge. So basically the percentage of balls and grinding media that we put into the SAG. And here you can see there that also that the measurements are less frequent because it's estimations done through different parameters. In fragmentation, for instance, the measurement is more frequent. But we can try and see what is the level that we get of throughput with 3 different levels. And here they are represented by green, red, and blue. And here's what we get. Okay? And this is quite interesting. And here is where the insight starts to happen. This is a graph of ball charge, as I mentioned before, and input fragmentation. Input fragmentation, let's for now take it as an input for us guys in the SAG mill. It's an input from the mine. Okay? As you would expect, by the way, colors mark the level of throughput. So more red is more throughput, and more blue is lower throughput. As one would expect, higher fragmentation moves into the higher throughput of the SAG. Of course, because it has to grind for lower periods of time. And the contour shows the historical levels at which we have observed these 3 years of data, right? So this mountain-like map shows you where you're operating. See the ball charge that it appears as if the optimal level is actually quite lower. This is not as low as it shows in the graph. It's moving from a 22% ball charge to a 19% ball charge, or actually 18% ball charge. And the increase in throughput is not huge, but it is significant, particularly when you're talking about the bottleneck. But just by lowering your ball charge, you're able to get to 2% more throughput in a bottleneck, in a SAG mill as large as Costa was. This was like $50 million of profit. So it's even though the percentages are small, and as you saw before, the parametric equations and the way we did things before get us 95% there. But this really lets us drive us home with this type of improvement. Here's another example. And here what I'm showing is for 3 SAGs. This is in the case of another operation in Chile, where you can see there you can see load, so how much I get of material into the SAG mill. This is very similar to the graph I showed before. Of course, if you put in there too much material, they don't have a space to be grinded. If you put too little material, then you don't get enough throughput. But the lower bar shows them, again, similar to the mountain graph that we saw before, where they are operating. Okay? And you can see here that absent of all other variables, we are operating at higher load for the throughput that if we want to maximize throughput. Okay? And this was something quite of a surprise for the mining company, because actually they had a heuristic of how to adjust and optimize and move to the optimal level of load. We can then expand this, and similar to what we did before, start to understand, okay, with load and percentage solids, which were the 2 key inputs into the control expert system, how far from optimal are we? And note that here we're seeing one scenario, which is one of the SAGs, a liner age of 4 months, so really close to the end of the life, and for a fragmentation below of an F80 below 3.3 inches. And then you can start building several scenarios with this for different liner age, for different percentage solids, for different levels of fragmentation. And what we did here was basically redefine what the optimal parameters were for this company. This, by the way, this is one of the operations of Antofagasta Minerals. Also a copper miner. Sorry, I'm from Chile, so plenty of copper examples there. But what we show with the model was that they were actually using higher percentage solids that they should, and higher load than they should be getting into the SAG. So they used the model and the parameters that we defined to readjust the ranges for the expert system. Now, the model predicted that this would get them a 6% throughput. It was actually lower. What we got after the several trials was around 3%, 2.5%. But the reason was not because the model was wrong. It was because it encountered bottlenecks downstream. So actually, the flotation cells started being the bottleneck after we implemented this. Okay? So that kind of sums up my SAG example. I'm probably going to skip my second example, but want to go quickly through it. We also did this with chemical processes. Here is an example from copper leaching. Copper leaching, what we did here is understood the problem there with machine learning has much more to do with the chemical composition and how it consumes the sulfuric acid for the leaching piles. And there, again, we were also able to see that the mining company was using way too much acid. And this was not because it wasn't optimal from a recovery perspective. It wasn't optimal from an economic perspective. They were actually getting better recovery and higher levels of copper. But the problem was that the return on the marginal acid after a certain level that we identified with the model was actually not economic. Okay? So as you can see, it starts to really get into very interesting insights for the mining operation. So I've done this now in several operations, and I wanted to quickly share with you on this final 2 or 3 minutes my insights from how to get this going. And for those that will be attending our lunch session, we're also going to discuss more in depth of how this can be implemented at your sites. But first is target the line pain points through hypothesis. I mentioned already the importance of hypothesis. It's also quite important to target the pain points. Not just take the data and start doing things just for the shiny toys syndrome. It's not about getting something cool with the data. It's about solving the line problems. Because if you are doing machine learning in operations, it has to be operations that drive this. It cannot be a digital center. It cannot be a data analytics center. It has to be a partnership with the operations. The guys in the line really don't appreciate if you come and say, I know how to solve your problem. You have to come with a hypothesis. Which brings me to my second point, which is get early buy-in with data visualization and discussion. And this is quite important. So the first time around we did this type of exercise, we did the hypothesis. And then after the model was done, we came back with those heat maps that you saw. And we were like, oh, look, there's a lot of insight. The guys from the line wouldn't believe us, because we jumped straight into the model. So the second time around we did this. Before jumping into the model, we started doing some visualization techniques, advanced big data visualization techniques using Tableau or Python to show them the data, the historical data, without modeling a thing. There were already many insights from that, because operators tend to know how they are operating in the day-to-day, but usually they don't take the step back and look at 3 years of data and understand, oh, look, as liner ages, I start speeding up the sag. I hadn't realized that because I hadn't seen this data in this way before. And that is very important for driving change. The third insight is perform short-term, low-cost trial periods. Again, if they don't believe you, just try to find a way to do a trial that will be low cost for them. And as they start to see results, then they start to engage further in this. Again, operations has to be a partner with the guys from data analytics. And finally, embed these results into standard operating procedures. I cannot stress this enough. We usually have a saying in BCG that when we do data analytics, it's 10% about the algos, 20% about the technology and the sensors, and it's 70% about change management. Without the change management, without managing how this will be used, there's not much change that will take place. It will just be, like I mentioned before, a shiny toy. So that's it. Thank you. And I don't know if we have time for Q&A. One? OK. Anyone?
How long does it take to put that together?
How long does it take? So usually it takes about 1 or 2 workshops to develop the hypothesis. And the type of insights that you just saw, it's about 6 to 8 weeks of building the modeling, showing the first batch of data, sharing with the operations, then building the model and doing the validation, it's 6 to 8 weeks. What takes a longer time is to actually run the trials on the site, on the actual equipment. And that's because it's actually very difficult to replicate the exact same conditions of fragmentation, ball charge, hardness, to say, oh, here I changed this thing. I changed the speed by 0.2 RPMs. OK, but if the fragmentation was slightly off, then we cannot really compare and make the trial comparable. So doing the trial is actually not trivial. Actually, I don't see anyone else lifting their hand. So
So it takes you 6 to 8 weeks to do it, and you do trials, and then what happens after that? How do you put it in production?
So basically, in the example I showed you before, they readapted the input into the expert control system. And basically, what they say is, we have these scenarios. So the liner is this old. We have this level of fragmentation coming from the mine, this level of hardness. Then we should be operating at this level of load and at this level of percentage solids. And that's just an input for the operators and for the expert control system to adjust to those targets. It's just, but you have to get it into the standard operating procedures. Sorry.
Are those live trials or are those based on historic data?
No, those was live trials. Yeah.
And that's part of the 6 to 8 weeks.
So the building of the model is 6 to 8 weeks. The trials can take, it depends a little bit on what you're changing and how is the ore coming from the mine. But it can take as little as 6 weeks or 2 or 3 months. It depends a lot on the type of ore and the phase that you're mining. Okay.
Yeah, I think we'll have to cut it off there, but I'm sure you can track down Agustin after. Thank you very much for the presentation.
Thank you.